lecture, we started from the sun and then to the atmosphere and to our planet. We discussed solar radiation trip from the sun to the location, specific location on the ground, and how to find the amount of insolation, the solar density, the flux approaching my collector, regardless if it is solar photovoltaic, if it's solar thermal. We went through process and equations and formula to calculate this amount, because this is the first step in designing any solar system. We talk about the type of error, the 4 types of errors, talk about the orientation, the transparent. We specify the amount of insolation based on some angles. These angles, example, are zenith angle, azimuth angle, declination angle, elevation, tilt angle, right? So we use these variables within equations to calculate the insolation on a tracking surface, on a stand-alone surface with an angle, stationary surface, on a horizontal surface. Now we know how much energy approaching a location here. Now let's go to the technology used to extract this energy, to capture this energy, to utilize this energy. Today we will start with solar photovoltaic. We will talk about solar photovoltaic here in different, let me say, lectures. We will start from the principles toward the systems, configuration, calculating electrical performance, behavior, and different applications. And I would like to start with this animation. Sorry. Okay, you like it? You remember this one? One day we may see it together. But now, what I want to say is, let me start this lecture with a question. Who's first went to the moon? This is usually a question I ask my students in different levels to excite them, to motivate them to the knowledge, creative, and innovation. And let me answer that question. It's not Gagarin or Armstrong. It's Hollywood. Hollywood is the first who went to the moon, and they went to the Mars. Till now, nobody went to the Mars, right? But in movie and TV series, we went to the Mars, right? We have trips in the whole universe. This is coming from where? From scientific imagination. And there is a startup from scientific imagination to the reality. This is happening. Can anybody close the door? the door, because it gets sound. So what happened is the scientists' imagination come up with a novel and new and significant ideas. Later on, 10, 20, 50 years, it will become a reality. And this animation, it's produced maybe 20, 30 years back. You watch it, right? You enjoy it. It's talking about the story, the whole story talking about using solar energy to save the world, because there is no energy in the world. Disaster happened, and humankind looking to have energy, source of energy. So the whole story, this series of animation, talking about solar energy. It's happening today. Today, we are not talking about China or US or Europe, we're talking about Oman. In Oman now, we just started a new solar photovoltaic system, solar energy system, which is 500 in Hebron, 500 mega, half nuclear power plants. It costs 400 million US dollar. Another 500 will come again and again. It had been announced. Few years back, 1,024 mega, more than 1 giga. What? Solar system in the south of Oman, in Miraat project, in collaboration with Glasspoint, the American company. It is the highest and unique solar system in the world, tough system. You got it? So we are not talking far from here, we are talking here in Oman. The story, the imagination started at that time. But it gets improved. We can see that today, wherever we go in Sohar, we can see there is signs using solar energy. There is street lighting using solar energy. There's some communication towers using solar energy. Even you here in the classroom, you have a calculator with a small piece which represents solar cell, which use light to produce needed electrical energy. Now, this takes me to say that the spectrum discussed last lecture, the solar spectrum, if you remember, we discussed it, we say that we have 3 parts, right? Visual part, infrared radiation, and ultraviolet, right? Now, the visual one, we will use it in our discussion for photovoltaic, for solar cell. We will start today in solar cell. Now, this imagination, okay, take me to brief you about first the history of photovoltaic. Some people, they thought that it's the future technology. But have a look, 1839. Oh, it's more than 100 years back, right? Yeah, it is. It's old technology. Photovoltaic effects by Becquerel started, and then later in 1870, Hertz developed the first PV, which is 2%, and in 1905, more than 100 years, okay? Einstein explained the solar effect, photovoltaic effect. And by the way, he won Nobel Prize based on his explanation, not on relative theory. And this is Einstein. So sound is not clear enough, but what happened is, in this speech, he explained the photovoltaic effect, okay? This is 1905, and later in 1930, another PV came from another material, which is not silicon, selenium, and in 1954, بالله, They manufacture the first solar cell using silicon-based technology with 4%. 4 years later, in 1958, the American used it in the first aircraft sent to the space, or the satellite sent to the space, which is called Vinger 2 project. Vinger 2 project is this project. Have a look. Small, let me say, satellites. It's like this size, as you can see. Like this size. You see? Small cell. But there's a wonderful story here because it opened the door for a new technology. This satellite uses batteries to provide the needed energy. And they put a solar cell, small solar cell, the one I show here, you can see, but they put it to be a backup. If the battery will not work or die, then this cell will take over. But they didn't know that it will take over. What happened in 2 weeks? In 2 weeks, the battery died, and then the cell starts providing the requested or required energy. And it keep working for another 7 years. The idea is to put a satellite in orbit to send signal to the Earth, to the receiver. Receiver is like this. You can see here, like this one. You do know what is this? Radio, right? It's the old version of iPad, okay? So what happened is they design or manufacture 5 copies of this satellite. One, they send it to the space, and another 4, they have it. I have here handing the version number 5 of the satellite by one of our colleagues in NASA, and he brought it in one of our meetings, and you can see here this satellite. Now, this satellite worked for another 7 years, and then stopped, but the let me say surprise for the humankind that this cell is working. They tested in the space, which is opened the door for very important technology, could be the future technology. Now after that, more work and investment to improve this technology. 1970, there is too economic crazy because of oil and wear and blah, blah, blah. What happened is this triggered the idea for investors, for countries, okay, for companies, to start looking for alternative to oil, because oil will become a problem for them. When oil prices go up or down, we face a problem. And you can see today we have a problem with oil, right? The prices went to 34, I remember 2 to 3 days back. Morning, I've been checking the oil prices were between 43 to 45. When I'm back home, at the end of the day, I receive update that become 30 for a barrel of oil. So imagine this high fluctuation, this high drop or high increase have very, let me say, negative impact on economics need to be considered. So it is not a stable energy, we can't depend. The reliability is very low. Solar energy come to be part of the future. Now in 80 decades, more progress happened, more material came, it's not only silicon. You know, silicon, as we are going to discuss later, is the second material available in our nature. It is in dust everywhere. Any country has silicon. And the technology proven very well. But in 80 decades, they try to look for more cheaper, more other materials to come and take over or to help and participate. So they try to use more material, they try to produce use more technology to produce different type, because the characteristics will change with the time. So as you can see here, crystalline, polycrystalline, monocrystalline, amorphous, and so on. More generations came. In 2000 to 2010, I tried to summarize the progress happening in this field, in the field of solar cell and solar photovoltaic. So what I found that there is a lot of effort spent in building. So PV become part of the building, so they call it building integrated PV. Okay? They start to look for energy consumption, energy reduction, energy saving. So this is one of the steps, or let me say the progress happening in this field. Another progress in the level of research. Now the research improved not only in the level of material used, but also the technology, how they reduce the process. the steps to produce solar cell or solar panel. Okay? Also, they try to produce more materials, they try to make it more cheap. Okay, and I will talk about the cost in a minute. And the third point is the prices. They look to reduce the prices. And I will give you example about the prices and the cost. If we back to 8th decade, 1980 to 1990, barrel of oil at that time cost between $17 to $20 per barrel. And at that time, solar cell, the 1 watt cost around $75. Progress, improvement in manufacturing, in efficiency, reducing the cost by reducing the process and improving the technology. Today, when we talk, as I mentioned, the oil price is fluctuating between 30 and 50 now. If we back early in 2014, it approached more than $120 per barrel. If you ask me about today, the price of solar cell per watt, for what? It is less than $1, $0.5 plus minus. You imagine from 75 in 80 decade, right? Today it is half plus minus, $0.5. It's very cheap, cheap like coal, okay? In 2010, I remember I gave this introduction in one of my presentations. It was in the United Kingdom, in the World Renewable Energy Congress at that time. So I gave it in 2010, the end of the year. So this is what is my impression. Huge disseminates, I really don't know. I cannot summarize because the progress is more than I can summarize it. Now it's become like Corona, like flu, right? Everybody interested. Nobody imagined that one day here in this region, in the GCC region, the 6 countries, where more than 1/3 of the oil produced here and globally produced here. Nobody expected that. They would be interested in solar energy. But this is the situation. They are. Now we can see the progress. 2040 in Oman, they expect 2030, 2040 in Oman, the vision talk about 30% in 2030 from renewable energy. Solar is the main. 2040, they expect it to be between 37 to 39. What we are talking about after 10 years from now, 2030, we expect that they will spend around 10 billion US dollar in renewable and mainly solar. So you imagine where you are going. You got it? So it's become important, it's become essential to go in this direction. Now after this brief history of the solar energy, also to remind you that this is the circle from my recent published book. You can read more about this information. However, I try to get this picture to see. This is the circle represent the energy consumption 2016. The yellow one here represents renewable energy. Still part, fraction of renewable more use their renewable energy. Now this part, if we break it down here, we can see it's coming from different percentages, from different sources. Biofuel, geothermal, solar energy, solar photovoltaic, solar thermal, wind, hydro, and other resources. And you can see here a comparison 2017, biofuel, hydro, wind, solar, and so on. So it's become part of the global energy profile. And it decreases in this country and decreases in another country, depending on the resources, on the interest, and the vision. And also, you can see here, still talking about the market and the progress. The progress I mentioned, you can see here in this graph. This is the prices and efficiency. Prices go down, but this is the efficiency. Okay, from 1870 and go up as a curve, as exponential. Here, when they started the first silicon with 4%, and here more progress came, and now we reach around 40%. You remember, we started from 2%. In 1954, they designed the first crystalline silicon in laboratory with 4%. Today, we're talking in the lab, 40. I will show the newest version, it talk about 48%. We go up. We go up, it means the production increase, the efficiency increase, the cost going down. which make it more exciting as a technology. This is all data talking from 1991 into 2009. You see the growth of world PV production. See the growth. But see the green one, it is the highest. Who's the green one? Oh, China. They took over. They did. And frankly speaking, the earliest, let me say, statistics talk about China is leading in many other technology, not only in solar, in wind, in some other hydro, and recently they also lead in corona. So what happened is there is an increment in the production of solar photovoltaic. After this introduction and background, after this history, let me start with more technical and scientific issues. I will start with the cell. Okay? By the way, this is the structure of our discussion today, and inshallah early next week. The cell is the main, let me say, element. We manufacture it, as I mentioned, from silicon. Here in this box, I have cells. These are 10 cells. You see, very thin, like a paper. You see here? Can you see this one? It could be broken, by the way, easily. You don't find this in the market, okay? Usually you purchase it from the market, solar panel. But this is the cell. Now this is the main part. If we put these parts together, okay, what we will come up with? We will come up with what we call it module. I mean, have a look. This cell is here, 1, 2, 3, 4, and here 9. We put them together, series parallel, because we need to increase the energy produced by the panel, right? If we put these panels together in series in this way, we call them, this module, we call them panel. If we put more than panel, we call them array. So the small one is cell, put them in one frame, what we come up with? Module. Put more than one module, what we come up with? Excellent, panel then array. You got it? This is the structure. Now how we manufacture it, from where it came, the solar cell and the solar module. Have a look, you remember this periodic table, right? Focus here more on this yellow. This yellow represents semiconductor. Do you remember from material? Level 1. We can classify them into insulator, conductor, semiconductor, right? Based on the electrical conductivity. Conductor is an element which can conduct the electrical current, while insulator cannot conduct the electrical. While semiconductor in between, if we treat it somehow, we can make it a conductor controlled one. You got it? So the focus was at the beginning of these materials. More focus on silicon. Why silicon? Because the second material available in our nature. They focus on this. We can't design and manufacture solar cell anywhere in the world. Since there is land, there is silicon. They start working with silicon. As you can see here, some of chemists are sitting here, right? This is your future. And people working only in silicon, because what happened is, today, most of our life is silicon. Your tab is silicon, mobile phone, computer, any new technology coming from silicon. So silicon is not only solar cell or electronic devices, but it is also the technology. This is one of the well-known here, produced every while by National Renewable Energy Laboratory, which is one of the main or the important laboratories in the world, is in the US. It's produced, you see, different here, coming up. Each color represents different technology. Polycrystalline, monocrystalline, tangent, as example, amorphous, These are solar cell or solar PV technology. It's going up from here, you can see 1957 up to 2019 here, or 2020. It is the newest one. What we understand from these curves, that the trend is going up with time. What is going up? The efficiency here. Let me check with you. What is the highest efficiency here? Can you tell me?
6.
Anybody can see this one? What is the highest efficiency here? 48, right? Excellent, 48. You remember? It was 2%, 4%. Now we're talking about 48. You may not find this in the market because, as you know, there is gap between the lab and the market. To commercialize, they need 10 to 20 years, but at least they approach this in their experiments. I advise you to have a look at the research produced by NERA. Now, back to the silicon as a part of our, or let me say, the main element used to manufacture photovoltaic. Silicon have 4 electrons in this way, connected by bond, right? In this way. You can see the red one here. This is one atom connected to another atom, to another atom, they make a crystal. Crystal, very pure crystal, right? It's not conducting the electrical current. I will show you how we will use it to make it conducting to the electrical current. And also, I would like to mention that the main technology for solar photovoltaic available today is crystalline, silicon, and amorphous. And if you want to compare between them to see the panel to directly say that this is crystalline silicon and this is amorphous, is the crystalline silicon is more pure, uniform, okay, beautiful. It's not, well, like a duck here, it's not uniform, not well distributed. You can see it's very well distributed, beautiful. Here it's like randomly distributed. You can understand it from here. In general, we will go to the atom and we'll talk about the conduction band, valence band, but let me just describe the features of each one of these technologies. Now, if you look to crystalline or polycrystalline, today they call it multicrystalline, the new version, high efficiency. So we expect the efficiency available in the market is higher than the other one, the amorphous. 14, 15, today it's available 18, even 20, okay? Established technology, because they started investing and doing research in this technology more than 70, 80 years back. So it's well proven, okay? And it's stable with time, when we put it outdoor, it's stable. The cost of production is an issue. They want to reduce it. It's reduced and keep reducing. Okay? We will talk about the cost maybe another 2-3 weeks from now. Low absorption coefficient and large amount of highly profile. The absorption of light coefficient is low, which is not good. They don't absorb all the light. And the amount of material used to produce the cell, comparing with amorphous, is higher. More material, more resources we need. While amorphous, if we compare it, it's high absorption compared with the first one. Also established technology. It has been, let me say, tested. One issue is it's flexible. It's not coming as a panel. There is panel, but usually it's flexible. In this way, you can put it in any way you want on the building. An excellent balance sheet, ecological seat, we're talking about it, and very cheap compared with the first one. Amorphous, very cheap. But from the other side, its efficiency is low, talking about 7 to 10. Please try to remember this as a, let me say, we'll put these numbers in our mind to compare later with other renewable energy technology. As example, here, have a look here. This crystalline, how much the efficiency? 14 to 22, right? How much the efficiency for the other one, amorphous? So very low, okay? Later we will see how much the expected efficiency for wind, for hydro, for otic, for geothermal, okay? Because we want to compare these efficiencies. One issue, then I will go to the doping, is that there is another idea saying why we use more material and why we use large size to have a solar cell to produce energy. We can't reduce, rather than we have this size, we reduce it to small size. Okay? Okay? But we use the optic, or let me say lenses, to focus, concentrate. You remember last time we talked about concentration? Rather than we have 1,000 watt per square meter, we have 10,000 as example, 20,000. So here we reduce the size of the solar cell, we save the place and we save the material, but the cost will be the lenses itself. And definitely this needs more work on the cell to handle this amount of energy and heat, and we need cooling, which increases the cost. Now back to the material. We mentioned that for conductor or metal, okay, it's conduct the electric current, insulator cannot conduct, semiconductor. If we go to the bond theorem, what we have? Have a look. We have valence band and conduction band on the level of atom. Between them, there is energy gap. Now, electrons for conduction, to say that this conductor is conducting electrical current, when we have more electrons here, you got it? More electrons here. See, the insulator is empty. No electrons, it cannot conduct. The electrons only in the valence band. Got it? Now, by the way, it's good to mention that you see this dotted line? Fermi level. It's called Fermi level. It's part of the energy gap. It could go up, it could go down. And simply, when the electron have enough energy to cross this Fermi, it will go to the conduction band. It's like atmosphere, a shield. While semiconductor, we have here few electrons compared with conductor and with the emitting for insulator. But here, we have space, which we will call it later as a positive charge, hole, which is a space looking to be occupied by electrons. Okay. Now this is the valence band, and this is the conduction band. When we take the crystal, the silicon, we take it as a pure, similar to the insulator. It cannot conduct the electrical current. We are going to make what we call it a doping. Put some impurity, like salt on salt, right? Some impurity, but not by hand, it will be computerized. As example, one atom from impurities for every million atom from the silicon. You got it? We will put some impurities inside, computerized in the lab. It will happen in the lab. Now, these impurities, before the impurities, this is the intrinsic, which is the pure, no impurities. Air is emitting or most emitting, and this is the gap, and this is the valence band. But either we are going to put impurities which produce electrons here with negative charge, or holes here with positive charge. So this with negative charge, we call it N-type, it means negative type atom or semiconductor. While this with holes, positive charge. So as I mentioned, we are going to do doping by putting impurities, either we put boron or phosphor. Why boron or phosphor? Definitely there are other materials. But because boron gives me extra electron, while phosphor gives me less electron. Oh, what do you mean? You remember when I talk about silicon atom? Yeah. We talk about silicon. How many electrons in the outer band? Right? The outer orbit, sorry. 4. Boron and phosphor, one of them have only 3. So we miss 1. And one of them have 5. We have extra 1. Got it? How it look like? Let me, I will, okay. Here, have a look here. Yeah. This is boron. and this is phosphor. You see silicon everywhere here. One atom, which is boron. Let me see. This electron from boron have a couple, or let me say, chain with the electron from this silicon atom. And this one also, and this one also. But this, here, there is empty, there is space, because we have only 3. Got it? This space, we will simulate it, or we will say like it's whole. What it do, I will talk about it. But let me come to the phosphor. Have a look at the phosphor. Also, 4 electrons connected to the nearby cells. But I have extra electron. Just a minute. This extra, what it will do? It will move through the network. So we have movement of electron, we have movement of charge, we have electrical current. Got it? Easy, right? But for boron, this hole, what is it? This hole would need to be filled by electron. So electron will be taken from another cell to put it here, which create another hole. And the other hole will be filled by another electron from another cell and so on. What happened? It's like the hole or the electrons together, they moved through the network. You got it? So in this way, we make a conduction of electrical current here and here. This called P-type and this called N-type. N-type is mean negative, P-type mean positive. N-type produce negative charge, P-type produce positive charge. Now, if we put them together, what will happen? Okay, have a look. We will put P-type and N-type together as a sandwich. In this way, have a look. Let's assume this is P and this is N. Let me ask you a question. In P, we have positive charge or negative charge? Excellent, positive. You see? What we put here? When we put them together, we will have like atmosphere, like Fermi level. This is the barrier between P and N. مرج البرهين يلتقيان بينهما برزخ. Correct. What happened is some of these negative charge, you see, will cross the barrier here, the bond here, to the other at the beginning. And some of the positive charge will cross here until they reach to the equilibrium. This is happening at the beginning. When we put P and N together, this is happening at the beginning. The electrical background students, they may understand what I'm talking about because it's the same diode principle. Got it? Now we reach equilibrium. Now this positive charge here is the main, this is the minor. The same thing here, this is the main, this is the minor. We call these major carriers, and this is minor carriers. Now what happens is, here it's become like a gate. Like a gate between them. Now this gate either compress or expand. Either it allows the current to flow or stop the current to flow. Okay? More information you can find it in my, as I mentioned, my recent book. And many books actually talking about this process. These are what I've been explaining here. Positive charge, MP, negative charge here, and then crossing, it makes this barrier between the two P and. Now what is the new one here? It will call P-N junction. What is P-N junction? P-N junction we manufacture. Have a look. Diode. Definitely you hear about diode. Transistor. Thyristor. And many other elements or parameters in these families. There are different types of transistor, different type of thyristor, different types of diodes. And the same thing, this represents the cell, solar cell, which we are discussing today. I think I will stop here, but I'm eager to listen to your questions. Is there any question? If you don't ask a question, I will make a quiz. quiz about what we discussed today. Yeah. Chemical. Silicon. It's your area. Gentlemen here. Any question? Okay, we'll stop now. We'll continue the second lecture. Thank you for attending.